population, we found your population mean, we found your population standard deviation, and we took the probability that a randomly selected person would be less than 6 feet tall. Okay, everything came off your population. Now we're going to introduce something else. We're going to introduce the relationship between your population and the set of samples that we keep collecting. Now, there's a good little Venn diagram smack in the middle of 261. 261.
That first is for 81.
Oh, I said 81?
Yeah.
I'm sorry, 261. Time to get new glasses. Okay, 261. You see the little Venn diagram there? You see all those little circles? Those are samples. Those are samples taken from a population. So from a population, they took 5 samples. See where they overlap a little bit? That means, say Michael was in sample 1, and I put Michael back into the population. I might pull Michael randomly and he might be in sample 5. So you can use the same participants. The thing is you have to stay within the same population, same characteristics, and the sample size has to remain the same. So that's just showing you that there's different samples, subsets of your population that you're going to pull. And from all those different samples, you're going to pull a sample mean. Now we're going to see some things happen and some things change. So as we look at this, we're going to find your sampling distribution is formed from all these groups of samples with the same sample size. This just means I have the same sample size, same characteristics. I take the same characteristics. They're constantly taken from the same population. Okay, and we call this a sampling distribution of sample means. These are kind of tongue twisters in here. It just means that if the sample statistic that we're looking at is going to be called our sample mean. And our sample standard deviation, we're going to write like this. That's all that this means. You're going to see all the samples, all their means, averaged in, take the mean of all the sample means. That's all it means. And then you're going to take the standard deviation. Yeah, it's kind of like a play on words all the time. It's like when I teach trig and I say, what's the sign, the S-I-G-N versus the S-I-N-E. Yeah. So, okay, so now, properties of your sampling distribution. These are where your samples come from. And remember, I'm taking equal samples out of my population. Remember, they're at random. So we find that there's 2 things we come across. We find that the mean of the population, this is my mean of my sample, is equal to the mean of my population. We're going to do some of these soon. Oh, the sheets.
You said that's your statistic and that's your parameter.
Your parameter that we use for your mean is this for your population. For your sample mean, sometimes they use this or this. But they start off using the U of X to be the mean of your samples. But when we go to write it, we'll write it like this. That stays the same. No change there. Here's the big guy. Your standard deviation of your sample is going to change based on your sample size. So n, every time we see a sample size, this is our n. Write this down because I can't tell you how many kids get confused with what is n. N is your sample size. Normally the problem always says, out of a sample of 100 cars, out of a sample of 50 robots, out of a sample of 25 earrings. It always usually tells you out of a sample of such and such size. Whatever size that is your N. So all this says is, we're going to take, this is your sample standard deviation. You're going to find this by taking your population standard deviation and divide it by the square root of N. That's all that means. And if I divide something, what happens to the number? If I divide 5 divided by 2, what happens to the number? It gets smaller. So what's happening is you're getting a smaller standard deviation for your sample. You're getting a smaller sample standard deviation. So instead of my population curve going like this, my population curve is going to keep the same mean. The mean's not going to change. But my standard deviation is going to push everything closer to the mean. It's going to go like this. Because I want to be a little bit more exact with my sample, because my samples could be off. I have to have a little play in there. So you're going to see that as we go to the left, your probabilities get a little smaller. As we go to the right, your probabilities get a little larger when we use your sample standard deviation. So there's two things you're going to look for when they call a sample, and you're going to change your sample standard deviation to be your population standard deviation divided by the square root of your sample size. Okay, probably doesn't make sense yet, so we look at these. So, here's an example in your book. See if I can shrink this way down. Let's see if I can shrink this down to get the whole page. I'm just going to walk you through this. I'm not going to have you do this, but I just want to walk you through it. I got it. Okay. So your book says you write the population values. So here's the values from your population. This is from your population. 1, 3, 5, 7 on slips of papers. You put them into a box and you randomly select 2 slips of paper. So this is your sample of 2. Therefore, N is going to be equal to 2. And you replace it each time. So I technically can get the same numbers over and over again, right? You list all the possible samples of size 2, and you calculate the mean of each. So if I made a tree, and I do this again, and I keep doing this, right? So I get 1 and 1, if you just kind of follow. 1 and 3, 1 and 5, 1 and 7. See it? Then I do the next branch. 3 and 1, 3 and 3, 3 and 5, 3 and 7. 5 and 1, blah, blah, blah. 7 and 1, blah, blah, blah. These are all the possibilities. 4 times 4 is how much? 16. So I have 16 possibilities. So from here, these are my samples of size 2, N is 2. I calculate the sample means. I just add them together, divide by 2. Add them together, divide by 2. I calculate my sample means. Then I'm going to take all my sample means, and I'm going to calculate the mean from all those sample means. So if you kind of take a look at what they're trying to show you, and they have it on the bottom. I don't know if I have it here. Now I have to kind of put it on here. If you calculate all your sample means, they show you that your sample mean, if I take all these means together, add them up, divide by 16, this came out to be 4. If I take these, add them all up, and divide by 4, this also came out to be 4. So it shows us that the sample mean is the same as the sample. Now our only difference is this. We're going to take the standard deviation that we would have found in here, This population standard deviation, they worked it all out, was radical 5. 2 point something or other. So they took this, and to find your sample standard deviation, they say take the radical 5 and divide it by the square root of n. And what's n? And what is it? 2. So we're radical 5 over radical 2. And radical 2 is like 1.4 something. So it works out to be 1.581 approximately. So it shows us that the mean stays the same, but if you work these all out in your L1, your standard deviation would come out to this. If I put all these things into my L1 and I did a 1-bear stat, my mean would say 4, my sample standard deviation would say this. Okay, so these are the sampling means. Will I ask you to do this? No, but I kind of like the way they had the concept of this. I kind of like their concept. They do another one with 3. If we do it with 3, obviously this makes it a lot larger. 3 times 3. And we're going to do 3 samples makes it a whole lot larger than this. So I just want you to just get the concept of this. I'm not going to ask you to do that one. That's just like a waste of time. Now, I don't know if you've heard it before, but this is like one of the major theorems of statistics. It actually has a name for this. It's called the central limit theorem. And that's what describes the relationship between the sampling distributions of your sample means, sounds like a tongue twister here, and the population that all those samples came from. All that means is I took all those samples, found their means, I took the average of all their means. I took the mean of the sampling means. Then I compared it to the population. This is where you make inferences about your population. Because you're going to see, I can ask everybody in this room what they got on their last test and take the average of what they got on their last test. If I want to ask every student that takes the college level statistics class and ask them what they got on their last test, how long do you think that would take me? Pretty long, right? Every student. So because that's virtually impossible, and then by the time I reach them, they would forget what their last test was. Obviously their last test would not be the same in the same time frame. I'm going to take a sampling of these students. And remember way, way, way back when we learned how to do sampling, everything is random. Sometimes we do clusters. Sometimes we do systematic. All those still stay into place. We don't have to worry about them. But that's where the samples come from. And most importantly, which that Venn diagram shows you, they come from within the same population. Jess, you can go home. Yeah. They come from within the same population. And they can overlap because as I pick 4 people here, as soon as I keep track of them, I throw them back into the population. I pick another 4, they can overlap. Depending on, how often that will happen is how big your population is versus your sample size. So there are 2 things that you have to remember. Is the mean is going to stay the same, but the standard deviation is going to change. Now, and remember when I kept telling you the sample size, we'll see how the sample size makes a difference. Here is where it comes into play. The population itself has to be normally distributed, or the sample size has to be greater than or equal to 30. And then we know that it is normally distributed. If you look at the bottom of 263, there's 4 boxes with blue graphs in them. I don't have them up here, but you have them in your book.
Oh, I see.
See them? So, if you take a look at number 1, any population distribution does not have to be a normal one, right? Haven't they had to tell us, actually, are we seeing in all the problems we do, our population is normally distributed, then we know we have a normal curve. But if they didn't tell us that, your population does not have to be a normal curve. However, if you look straight down underneath it, if we took a sample out of any population and that sample size is greater than or equal to 30, we automatically have a normal curve. Now the right-hand side of it says, if you take a given normal distribution, I tell you this population is normally distributed, and now I take a sample size out of a normally distributed population. My sample size will be normal. I know this is dry, guys. You have to kind of bear with me. We're going to get to see this in a second. Okay. So why am I telling you all this? What is she trying to get to us? I'm trying to get you to understand this is a major theorem because it will almost always be impossible for you to survey your population. So you'll almost always be taking samples of it. Same thing if I said ask every student in the school what they think of a four-day school week. No, you're taking a survey. Do you like it? Do you not like it? You have to sample. You have to ask everybody in the school. That's over 3,000 kids. So would I really want to do that? No, I probably want to make samples. Good. Sample maybe 100 kids randomly. Get another sample of 100 kids randomly. Do my random samples. So here's how this has an effect on you. Cell phone bills for the residents of the city. This is my population. My residents of the city, say population, have a mean of 47 and a standard deviation of 9. Did I give you, no, what I wrote. Now, random samples, here's the word random samples of 100. Therefore, what's n equal to? 100. This is my sample size. Random samples of 100 are drawn from this population. Not just one, but a number of them. But they're all a size 100. Now, I take all those samples and I take the mean of all those samples and I take the mean of all those means. So the mean of the sample size is determined. The mean of your sample size is going to match the mean of your population. So we know this is going to be 47. So, this is also the standard error of the mean sampling distribution. This is what's called your sample standard deviation. They refer to it as the standard error of the mean of the sampling distribution. The words are so annoying in this, but bear with it. All we're going to do is take the standard deviation from the population and divide it by the square root of how many are in your sample. So it's technically going to make it smaller. So we're going to take your standard deviation of 9 and divide it by the square root of 100, which is 10. So look what happened to your standard deviation. It went from 9 to 0.9 to under 1. Now, if I took a look at the population, if I took a look at your curve, here was your 47. If I added 9, here's my 47. If I added 9, 56, 65, and so forth, right? If I do the green one, and I'm still 47, and I add 0.9, 0.9 would give me 47.9, would give me 48.8. Look what's happening. It's looking like this. It took them all and squished them in. They made them closer to the mean. A smaller standard deviation gives you less variance, makes you closer to the mean. Question? Yes. I thought you were going to ask me a question. Okay. Now, I took a random sample of 100. This guy says, use the same scenario, use the same population mean, use the same population standard deviation, but now instead use a sample size of 64. both cases, I know I can do this. I know I'm allowed to use the central limit theorem because my sample size is automatically greater than or equal to 30. So because of that requirement, I know I have a normal curve. So I'm able to use this. Now, if I do this, what's the mean of my sample if I change the sample size to 64?
1.125.
Nope, first give me the mean. 47, the mean is going to stay the same. And hang on to yours, Michael. Now I'm going to change the standard deviation to divide by the square root of 64, which is 8. And what'd you get, Mike?
1.125.
25. Good. So look what happens. This is my standard deviation for my sample. Give me a rule here. The larger the sample, the lower the sample standard deviation. The larger the sample, what happens to my mean? Stays the same. Nothing happens to my mean. But the larger the sample, the more exact I can get. So I'm pulling them in even a little tighter on my sample. The more you sample, the better your sample should be, right? If I only took 5 out of here, the chances of getting the people the same height, for instance, would be pretty good. If I took 10 out of here, I'd get more of a variety, right? So the larger the sample, the closer to the mean, the smaller the standard deviation. Yeah? So the what? Well, I don't know if I would make a proportion, but they're kind of, I mean, you could say they're kind of proportional without really an exact proportion. Okay. So, now here's another situation. Assuming the heart rates of all 20-year-old athletes are normally distributed. This time they told us these are normally distributed. So we know we can use the central limit theorem. With a mean, this is your population, with a mean of 135 beats per minute and a population standard deviation of 18 beats per minute. Here's my sample. Notice how it says random sample of size 4. The reason they had to tell us this was normally distributed is because my sample size was less than 30. If it's greater than or equal to 30, it automatically, that sample will be normally distributed. If it's less than, they have to tell us that our population was normally distributed. Now we know that our sample will be normally distributed. So what does this 4 represent? What letter? N. So my mean from my sample will become my mean from my population. That's all this means. And my standard deviation for my sample will say take the population divided by the square root of 4. If I divide by the square root of 4, that's like 2. So I'm just cutting it in half. I didn't make it too small, I cut it in half. It still brought me, instead of having a curve that went like this, it brought me a little bit closer to the mean. The thing is, your mean never changes. Your mean stays the same. But your standard deviation pulls it a little closer. This still covers 100% of your curve. It just squished it in. If you took something, like if you filled up a box with sand, and then you made that box narrower, where would your sand go? If I took it and I decided to take this flexible box and to push it in, where does my sand go? Up. It's going to make a little mound here because I got to somehow get rid of this. I got to somehow push it together. So it forces your curve to narrow and come up. So it's the same area. We didn't change the amount of sand in that box. We just pushed it up.
So is it still normally distributed?
It's normally distributed here because if your population is said to be normally distributed, then automatically your sample is normally distributed. If it says your population, your sample size is greater than or equal to 30, then it is normally distributed. Now, we could change this problem. If they didn't tell us this, and they just gave us a sample size of 4, we have to stop and say, sorry, we can't do this. We don't know if this is going to be normally distributed. Okay? So you guys try it 3. All I want you to do is come up with your mean and your sample standard deviation. This is dry, I realize it, but this is the most important part of this piece. And just like you don't like to sketch, kids that don't get this and don't sketch, okay? The mean is going to stay exactly the same as your population mean. What we come up with for a standard deviation for your sample? 0.05, good. We took your standard deviation from your population over the square root of n. Now, why were we able to use this? My sample size is only 16. It's less than or equal to 30. How did we know that our sample would match a normal curve?
It's less than 30.
What?
It's less than 30.
Well, if it's greater than or equal to 30, then we can assume that it is normally distributed. But this guy is less than 30. So why were we able to use the central limit theorem here? Because it said our population was normally distributed. So if our population is normally distributed, any samples from that population will also be normally distributed. So you're going to take your population standard deviation and divide it by the square root of n. So all I'm asking you to do right now, I'm changing your world around a little bit. We're getting off of your population and we're looking at your samples. Yes?
So whenever it's a sample size, we have to do all of x equals all over
Yep. Yep.
Okay.
And then if it's from the population, no, we leave it alone. Okay, so here's a little assignment to do. Okay. So we